Alright, hello everyone, welcome back to another video, and today we are going to be taking a look at a flame problem, and what we're going to be trying to do is we're going to try and find the temperature of this flame right here. I know I only had a green marker here, so it kind of looks more like a volcano than a flame, but just sort of imagine that we have air flowing in from this direction and natural gas flowing in from this direction, and it's going to be going through a combustion reaction up here. And we are going to try and find the temperature up here using some energy equations. And yeah, we're going to go ahead and hop into this problem now. So this natural gas over here is going to be 95% methane, 4% ethane, and 1% propane. And then the air over here is just going to be the standard air that we breathe in every day. It's 79% nitrogen and 21% oxygen. I know there's a few other molecules that are present in the air, but those are at small fractions, so we are going to go ahead and count those as negligible, and we're only going to go ahead and use those ones right there. Now, there are two important things to know about this problem. This problem is going to be steady state, and it's going to be adiabatic, and pretty much what steady state means is there's going to be no change in energy with respect to time. So what that means is the enthalpy of the reactants over here is going to be equal to the enthalpy up here when it gets to the products after the combustion reaction. And what adiabatic means is that there's going to be no energy being lost to the surroundings, all right? All the heat is going to be maintained within the system, all right? So the only two energies that we're going to be left with is going to be the internal energy of the system plus work done. And we're going to get an enthalpy equation out of that. So that's going to be dH is going to be equal to U, the internal energy, plus PV, which is going to be the work done. Alright, so we're going to go ahead and use this equation right here. Alright, so we do know that the enthalpy of the products going into the reaction is going to be equal to the enthalpy of the products going out of the reaction because, again, it is a steady state reaction. So we're going to go ahead and do the enthalpy going in is going to be multiplied by a change in the mass going in, and that's going to be equal to the enthalpy going out times a change in the mass going out. And enthalpy is a joules per mole, so we are going to need to figure out what the ratio for all these moles is going to be. So we're going to go ahead and do some stoichiometry to figure out the ratios so we can plug this into a Python program later on and solve a root function to give us the change in the temperature for this reaction. So for the first one, we're going to go ahead and do methane. Alright, so we are going to go ahead and jump into our stoichiometry equation for our methane right here, and methane is going to be CH4. And that is going to be reacting with oxygen in a combustion reaction. And nitrogen is also going to be involved in there because that's coming in from the air, but that's not going to be doing much of anything in these reactions. It's mostly just going to be a spectator. So we'll go ahead and put our products on the next line. And this combustion reaction is going to form CO2 and water. And then it's also going to have nitrogen again down here. And now we're going to go ahead and get to balancing. So as you can see right here, we have 4 hydrogens on our reactant side, but only 2 on our product side. So we're going to go ahead and multiply our water by 2. And that leaves us with 4 on the reactants and 4 on the product. So the hydrogen is good. Next, we're going to take a look at the oxygens. We have 2 oxygens over here in the reactants, and then we have 2 over here from the carbon dioxide and 2 over here from the water, so we have 4. So we'll go ahead and multiply the O2 so we can get 4 on each side, so the oxygen is now balanced. And now, as you can see, we have 1 carbon on the reactants and 1 carbon on the product, so that is all balanced out. And so yeah, all of our carbons, oxygens, and hydrogens are now balanced. Now we're going to take a look at the nitrogen. So to get our moles of nitrogen, we know that it's going to be in a 79 to 21 ratio over here with the oxygen. So what we can go ahead and do is multiply it by the moles over here on our oxygen, and then multiply it again by the 79 over 21 ratio, because we know that the nitrogen and oxygen are always going to be related to each other in a 79 to 21 nitrogen to oxygen ratio. So we're going to go plus 2, and then 79 over 21. Squeeze that in there. And then 2 times 79 over 21. And there we have our balanced equation for the methane. And now we'll go ahead and do the one for ethane. Ethane is going to be C2H6, and it's going to be the same reaction otherwise. All that's changing is we are going from methane to the ethane. So that's going to be plus O2 plus N2, and that's going to be forming CO2, water, and nitrogen again. Nitrogen is again not doing anything in this equation. Alright, so we'll go ahead and get to balancing. Over here we have 2 carbons and 1 carbon on our products right here. So we'll go ahead and multiply our CO2 by 2. So we can get 2 carbons on each side like that. And then after that, we are going to go ahead and we'll take a look at our hydrogens. So we have 6 hydrogens in our reactants and 2 over here. So what we're going to go ahead and do is we're going to multiply our water by 3 so we can get our hydrogens balanced. So now we have our carbons and our hydrogens good to go. All we need to take a look at is the oxygen. So we have 2 oxygens in our reactants and then 4 plus 3 over here, so that's going to be 7. And to get from 2 to 7, we would need to multiply our 2 by 7 over 2. So it's going to be 7 over 2 oxygens. That gives us 7 oxygens in our reactants and 7 on our products, so that's going to be all balanced out. And now all we have left to do is take a look at the nitrogens again. And it's going to be the same thing we did up here. We are going to multiply it by our mole ratio of our oxygen, and then multiply it by the ratio of the molecules in the air. So it's going to be times 7 over 2, and then times 79 over 21 again. So it's going to be 7 over 2 times 79 over 21. And that is going to give us our nitrogen. And we'll go ahead and do the same thing up here. 7 over 2, 79 over 21. And yeah, that is going to be our stoichiometry for the methane and the ethane. We're going to go ahead and leave out the propane for now. We don't really need to do that. I'll show you why later on in our Python coding. But we're going to go ahead and ignore that for now. We're only going to need these 2 when doing our Python program. And yeah, now we're going to take a look at enthalpy in greater detail. Go ahead and erase our stoichiometry over here. So we know our enthalpy is going to be related to the change in the temperature and the change in the pressure. So we're going to write an equation out for that. We're going to go change in the enthalpy. That is going to be related to the change in enthalpy due to the change in temperature at a constant pressure, and then the change in enthalpy due to the change in pressure at a constant temperature, alright? So this is going to be dHT at a constant pressure, and then it's going to be flipped around on the other one. It's going to be the change in pressure at a constant temperature. Constant temperature, and then that's going to be dP. Alright, and we can go ahead and cross this one out, because we know it's a steady state equation, all right? These are, or it's not steady state. One thing I forgot to mention is that we are assuming that these are ideal gases over here. So the molecules are not really going to be interacting with each other. They're going to be pretending they don't exist. So the pressure isn't really going to be changing. It's going to be remaining constant. So we can go ahead and cross this equation out. And we're just going to be left with this expression right here. And that's what we're going to be using to code in our Python. This dt right here is what we're going to be solving for. That is what we're looking for, the change in the temperature. And we're going to use this energy balance equation right here to solve for our temperature, and we'll go ahead and jump into that now. Alright, here we are in our Python code, and as you can see, I've gone ahead and copied over our GitHub file over here that is going to be keeping track of a lot of our information for all the molecules in the natural gas in the air so that we don't have to write out a bunch of variables. And what we're going to go ahead and do now is we're going to go ahead and look at the equation that we wrote out on the whiteboard earlier. And one thing I forgot to mention is this change in the enthalpy over the change in temperature. That is also represented by the specific heat of a compound as pressure stays constant. All right, so we're going to go ahead and write that out as Cp. And now we can't assume that the temperature is going to be remaining constant. All right, it's going to be changing a lot. So, which means Cp is also going to be changing, all right? Because the temperature is going to be very big in this equation. So, what we're going to have to do is we're going to go ahead and have to integrate this equation right here, all right? And when we integrate dH, that is just going to give us the difference in enthalpies. So that's going to be really easy. And the next thing we're going to need to do is we're going to need to integrate Cp, the specific heat, with respect to temperature. Alright, so we're pretty much going to be integrating this right here with respect to temperature. And we're going to be doing that using this equation right here, alright? This is going to give us the integral for the specific heat. And as you can see, there's a bunch of constants in here. We have 5 constants. And those are going to be different for all these compounds over here. So if we take a look over here at equation number 107 from our CHE tools file, as you can see, it is the ideal gas heat capacity in joules over kilomoles. And we have 5 coefficients right here. That's going to be A, B, C, D, and E. And it's going to be different for all these compounds. So yeah, we're going to go ahead and use these. We're going to go ahead and integrate over here. We're going to go ahead and integrate this equation right here. And it's going to be super easy. First of all, the integral of A with respect to t is just simply going to be AT. And then we'll go ahead and integrate this expression right here with respect to a t, and we'll go ahead and integrate this one as well with respect to t. And I've already had and gotten those written into Wolfram alpha. So the integral of this first expression right here, this b times this fraction squared, that is going to be over here. So that is going to be c cotangent h of c over t. And using some, so we're going to go b over t, and we're going to put that over the tangent of c times the tangent h of c over t. So we'll go c tan h times c over t. Alright, so we are back now, and we're going to go ahead and take the integral of this last expression over here. And we also have that one written out in Wolfram alpha over here. So that is just going to be dt multiplied by this negative e. And since there's a negative, we're just going to go ahead and subtract that. So that's going to be times e tangent h. times E over T. And there we have our integral right there. And now we're going to go ahead and hop into our Python and write some functions out so we can eventually solve for the temperature of the flame. Alright, so we know that the change in the enthalpies is going to be equal to this equation that we've gone ahead and written out, the integral of this right here. And so we can go ahead and use some functions so that they can kind of solve for each other at the same time and kind of bounce off of each other. So we're going to go ahead and jump on into our Python, and we're going to define a function called the integral CP, and we're going to go ahead and input a temperature for that. And basically all this is going to do is this is going to return what we just written out right here. So we're going to go, and since these A, B, C, and so on, all those constants are going to be different for each compound over here, we are going to have to use our CHE props over here. So we are going to go P dot CP IGA. We can't just we can't just write it out because it's going to be different for all of the compounds. So we're going to have to put this in here, and we're going to multiply this by T for the first one, and that is going to be our first term. And we're going to go ahead and write out the rest of this over here. Alright, so I've gone ahead and finished writing out the full expression for the integral. And the next thing we're going to want to do is we're going to define our function for the enthalpy at a given temperature. And we are going to basically just return the enthalpy of formation of an ideal gas, right? Because starting out they are in the oxygen and nitrogen are in their O2 and NO2 states. So they're going to be in their ideal state. So that's going to give us that, and we have to do our P dot for those as well. And then we're going to add that to our integral CP of the starting, or the temperature. This T right here is going to be the temperature of the flame, and then that's going to be subtracted from the integral CP of the starting room temperature condition. So that's going to be 298.15. And yeah, that is going to be our expression for the enthalpy of T. Let's go ahead and get that shift return, make sure that's all working good. And next thing we're going to do is we're going to do some matrix math. Since we are going to have a lot of stoichiometry and ratios and fractions going on, we're going to do some matrix math to make our lives a lot easier, and we'll jump into that now. So I've gone ahead and written out our stoichiometry equations that we did earlier on the whiteboard, and before we get into solving the equations to find the temperature of the flame, we are going to need to do some matrix math with our natural gas. This is because it's not just one pure compound that is going to be going into the reaction. It's going to be a mixture of methane, ethane, and propane. Again, it is 95% methane, 4% propane, or 4% ethane, excuse me, and 1% propane. And it's going to be a different amount of carbons and hydrogens reacting for each of them. So we're going to need to do some matrix math to figure out what the exact proportion of the carbons and hydrogens is going to be for this reaction. And to do that, we're going to be doing some matrix math. So we are going to go ahead and hop on over into our Python right here. And we are first going to create a matrix over here for our percentages, our proportions of each hydrocarbon. So we're going to go ng mole equals mp dot array. And then this is going to be a 3x1 matrix. It's going to be 0.95, then 0.04, and then 0.01. And that is going to add up to our 100% natural gas. Again, it's the 95% methane, the 4% ethane, and the 1% propane. And then the next array we're going to want to create is the number of atoms of carbons and hydrogens within each specific hydrocarbon. So we're going to call this matrix atom rations, and then that's going to be equal to mp.array. Alright, and then this is going to be a 2 by 3 matrix right here. And then this is going to be 1 and 4 for the first one. This is representing the methane. We have 1 carbon and 4 hydrogens for this one. And in the next one, we're going to have 2 and 6, representing the ethane with the 2 carbons and the 6 hydrogens. And then lastly, we have 3 and 8 for the propane. And there we go. We have our matrices set up now. And now we're just going to multiply them together basically to get a 2 by 1 matrix that is going to give us the number of carbons and the number of hydrogens. And first, before we do that, we'll go ahead and think about this a little bit. Since this mixture is 95% methane, and methane is 1 carbon and 4 hydrogens, we can expect this, if everything works out right, it should be a little bit over 1 carbon and a little bit over 4 hydrogens. Not a whole lot more. It should be just right around those numbers, but a little bit up, because again, it is 95% methane, and the 2 other hydrocarbons are a little bit bigger, so they will bring the numbers up by a little bit, but not by a whole lot. So we'll go ahead and do our multiplication here, and we'll go ahead and do NC to represent the number of carbons and NH to represent the number of hydrogens, and that is going to be equal to Ng mole. And then to multiply that, we use the at symbol, and then that's going to be atom rations. There we go, and see if that's working. Invalid syntax. What do we have here? Let's see, maybe do we need to put one more around all of it? Let's see, is that working good? Oh, we forgot to put one right there. There we go. Get that all deleted away. Array takes from 1 to positional, but 3 were given. Alright, I'll be right back once I get this sorted out. Alright, so we got this all squared away. We were missing an extra bracket over here, but now that we have that in place, that is working well. So we'll go ahead and test this out, see if she's working alright. And yep, carbon is definitely working good. As you can see, right as we expected, it's going to be a little bit above 1 because it is 95% methane. And this, we'll test out the NH. This should be right around 4 for us. And yep, there we go. That's working nice and dandy for us. So we have our proportions for our carbon and our hydrogen working out good. Alright, get another code box. And what we're going to go ahead and do now is we are going to want to go ahead and use our stoichiometry equations to figure out the proportions of the different molecules as they relate to each other, so that our Python can use those numbers to figure out the right numbers to use when solving for the temperature later on. Alright? And the first thing we're going to want to do is we're going to go over here, and we're gonna try and find relationships between compounds on the right side and compounds on the left side. And the first one we're gonna do is we're gonna take a look at the number of CO2 molecules over here. And as you can see, the number of CO2 molecules is going to be related to the number of carbons over here on the left side. So on the right side over here, we have 1 CO2 and then 1 carbon over here. And then on the bottom equation, we have 2 CO2s, and then on the left side, we have 2 C's again. So that's a relationship 1-to-1 right there. So it's going to be NCO2 is going to be equal to NC. Alright, and then we'll go down to the next line, and the next relationship we're going to look for is we're going to look for a relationship with water in another molecule. And as you can see, the number of water molecules is going to be half of the number of hydrogen molecules. Alright, so we have 4 H's over here and then 2 waters. And then on the bottom equation we have 6 hydrogens and then 3 waters. Alright, so that is going to be a 2-to-1 hydrogen to water ratio right there. So that is going to be our second relationship. So we're going to go NH2O is going to be equal to NH over 2. Alright, and then lastly we are going to look for a relationship with N2 over here, alright? And N2, as you can see, is going to be related to O2, alright? And it's always going to be the number of O2s multiplied by the 79 over 21 proportion that they have for the air, since the air around us is 79% nitrogen and 21% oxygen. So as you can see, this is 2 times 79 over 21, and the exact same thing over here, just multiplied by the 79 over 21. And then again, the nitrogen and the oxygen have the 7 over 2 coefficient in front of them, with the just added 79 over 21 for the nitrogen. So that is going to be the proportion we use for that. So we're going to go NO2 is going to be equal to 79 over 21 times N2. There we go. Alright, so we did have a little bit of a mix-up in our equation down here. This should be N2 and then O2 over here on the right side. So we got that all squared away, but now we're going to need to find the real equation to find the number of O2 molecules. And if we go back to our stoichiometry equation over here, we can see that there are 2 O2 molecules over here, and if we multiply the H2O by 1/2 and then add it to the number of CO2 molecules, we would get 2, alright? So you could do 2 times 1/2, which is going to equal 1, and then plus the 1 CO2 molecule, that's going to give you 2 right there, and that equates to 2 oxygen molecules, alright? So we'll go down to the second equation, and we'll do the same math. We'll go 3 times 1/2 is going to give us 1.5, and then we're going to add 2 to that, and that is going to give us 7/2. And if we look over here on the left side, we have 7/2. So that is going to be the equation, the proportionality that you would use to solve for the number of O2 molecules. It's going to be NCO2 plus 1 over 2 times NH2O. There we go. Alright, so one of the parameters we were given at the start of the problem that we did forget to account for is the excess air that is going to be involved in this reaction. So there's actually going to be more air than is required for this reaction, and we are given a percentage for that, and the percentage is 20%. So we'll go ahead and include a variable for that. We'll go excess air, and that is going to be equal to 0.2. And the way that we're going to account for this is we are going to multiply the number of NO2 molecules by this excess air variable plus 1. So that's going to be multiplied by 1.2 or raised by 20%. And that is how we're going to account for the excess air within the reaction. And now we're going to create some arrays for the number of moles going into the reaction and then the number of moles of the final products coming out of the reaction, alright? So we're going to create a couple of arrays for that. We're going to go the moles in and the moles out. And for the moles in, we are going to use a concatenate function, I believe is what it's called. I believe that is how you pronounce it, because we are just going to be taking our Ng moles for our natural gas that we used earlier for this, and that is going to be so that we don't have to go through and do it again ourselves. We can just add this one. So we're going to go Ng mole. Then we're going to add another array onto it, and this one is going to be our number of moles of CO2, And they turn the lights out on me again. Alright, so this is going to be the number of moles of O2, and then the number of moles of N2, and then we're going to go 0 and 0 after that, because this is going to represent the number of moles of the carbon dioxide and the number of moles of water. And since those are just final products, and we're not actually starting out with any in the initial conditions, it's going to be 0 because it's non-existent at the start of it, so we're just going to go with 0. And then for the moles going out, we're going to do NP array. Since we are not adding two arrays together, we are just going to be creating it. And then for that, we are going to go 0, 0, 0 to start off with. Because all of the natural gases are getting used up within the reaction, there's not going to be any left. Since the air is going to be the reactant that is in excess, these are all going to get used up in finality. And then after that, we are going to go the number of moles of O2 times the excess air. So that's going to be 0.2 or 20% of the moles that we started off with. And then that's going to be multiplied by N2. And then this is going to be the number of moles of carbon dioxide and the number of moles of H2O, and that's going to be our number of moles going out. Let's just make sure that we have everything lined up. So we have our natural gases starting out, and then followed by the O2, then the N2, and then the carbon dioxide and water. So yeah, it's looking like we've got all that lined up correctly. Let's go ahead and shift enter, make sure all of our syntax is right. Excess air is not defined. Alright, one quick thing I want to mention before we go on is that we only need the excess air equation within our O2 equation. We do not need it within our N2 as well. So that was a mistake that I made earlier on in the video. We should only have the excess air equation for the O2. Alright, so I did find what our issue was here. We do need to include a multiplication sign. Let's see, make sure that's all working good. Yep, there we go. And now what we are going to be able to do is we are going to create our temperature function. So we're going to go define temperature, and that's going to be input with a vector. And then for this, we're going to go t is going to be equal to the first unit within the array. And basically what this is going to return right here is it's going to be the dot product of the enthalpy and the moles going out, and the enthalpy of the temperature starting and the moles starting. So we'll go ahead and write that out. So this is going to be equal to NP dot, and then this is going to be the enthalpy of the temperature. That's this function right here, and then that is going to be along with the number of moles going out. So this is our final enthalpy and our final number of moles right here, as you can see. And then that is going to be subtracted from another dot product, and this is going to be our starting conditions right here. This is going to be the dot product of the enthalpy of our starting temperature, which is 298.15, which is room temperature, and that is going to be dotted with the number of moles going in, like so. And that should do it for our temperature function. See if that's working well. Yep, there we go. And now we are going to use our root function here to solve for this. And all we have to do here is use temperature, and then we'll include our guess here. We'll go about 20,000 for our guess. It's going to be high up there. It is a flame, so you know it's going to be hot. And then we'll go .x, and then we want it to return the 0. And we'll see what we're working with here, see if it's given us the right answer. And name vec is not defined. Alright, we'll get that uncapitalized. Alright, there we go. Alright, so this temperature that we have over here is much too low, so we did make a mistake somewhere within our code. And the mistake that we made, I did figure out. It was over here within our integral CP. Let me pull this up right quick. I'll show you this in the files. We had a units mistake. One of these was in kilomoles and the other one was in moles, so we were off by a factor of 1,000 for one of these, which was screwing with a bunch of our equations. So we'll go ahead and pull up these. Let's see, what do we want? We'll go ethane. We'll pull up the ethane right quick. Take a look at that. So over here we have the ideal heat capacity, which I believe was this one right here. That is in joules per kilomole, but down here in our enthalpy we were doing joules per mole, so that's just a quick and simple easy fix. What we're going to go ahead and do is divide our integral CP function over here by 1,000, like so, and that should square everything away. We'll get this into a joules per mole, and that should make everything squared away. So we'll go ahead and run that, and we'll just go ahead and run everything else while we're at it, make sure everything is good. Here we go. And another thing we also did is we were off on our guess. It's not going to be 20,000, it's not going to be nearly that hot, it's going to be around 2,000. So we just want to make sure that we have the right guess, so it starts the root function at a closer number, so it solves for the correct root. So we'll go ahead and run this. And there you go. That is going to be the final answer right here. The temperature of the flame is going to be 2,063 degrees plus a little change. And yeah, that is how you solve for the temperature of an adiabatic flame. And make sure to leave a like and a comment on the video if you enjoyed. Have a good one.